to the afternoon session, in particular for the ones who are here. I'm very happy to introduce Martino Grasselli from Padova and Paris. He's going to speak about fast hybrid schemes for fractional Riccati equations. Rough is not so tough as the subtitle.
Thank you, Joseph, and thank you, everybody, for your kind presence here, in particular the organizers of this beautiful conference, George, who is multitasking now. And, I have to apologize for the title, which is quite a provocative sentence. Rough is not so tough. This is an idea of Gilles Pagès, who made most of the work. So I'm humbly try to explain to you what Gilles explained to us. So the other collaborator is Giorgia Calegaro, a colleague of me in University of Padova. So which is the idea? The idea is that, nowadays, it seems that there is a new paradigm. The volatility is rough. I don't say that I'm skeptical, but I'm still open to other possibilities. So in my opinion, maybe the estimation of the H, so the Rth exponent, is still under investigation. So I don't take a clear position on the case where H is 1/2, is greater than 1/2, is less than 1/2. And according to that, we have the presence of long memory, anti-persistence of a pure Brownian motion, classical Brownian motion. So we would like to give a framework in order to have some numerical scheme which hopefully will represent a new benchmark instead of what is currently used in order to solve this kind of equation I'm going to explain. So the fractional Riccati equation, which is the Adams schema, very, very slow, no efficient, and sometimes useless for financial purposes. So we will provide a framework for which you can choose the exponent H as you like. So there is first of all, we have to set up the framework, and in particular, we will focus on a particular stochastic volatility model, so the rough the rough Heston stochastic volatility model. We will recover the corresponding Riccati equation associated to the problem of finding the characteristic function, and we suggest this new numerical scheme. And we'll see some results, of course. First of all, the idea is that why Heston model bar? That is still quite used in practice. There are many properties for which, we can justify the success of this model, not only in literature. The fact that, for example, it gives the possibility to have a time-varying volatility with leading to skewed implied volatility surface, so which is quite nice in order to fit the implied volatility surface. It leads to fat tails, but the most important thing is due to the, numerical tractability, in the sense that it admits closed form solution for the characteristic function of dog price. So which means that it leads to Fourier pricing, and so calibration is also feasible. Well, the rough Heston model replaces the Brownian motion driving the volatility with the fractional Brownian motion. And according to some recent developments, so Omar and Mathieu, Jasson and Mathieu as well, Gatteral and co-authors, it seems that there is, in some financial series, evidence of the fact that the X exponent is, highly less than 1/2, so leading to the so-called rough path for the volatility time series. Well, this is also supported by estimation with high frequency data, and there is a quite, a clear cut with respect to the previous literature, where till 25 years ago, they started to introduce fractional Brownian motion, not really on the volatility, mostly on the underlying, so leading to some arbitrage possibility because the underlying is no more semi-martingale. But okay, if you introduce in the volatility instead of the underlying, you still have some consistent model with the classical no-arbitrage paradigm. And they estimated in many historical series, not only on equity, but also interest rates and also in commodities, they systematically estimated H greater than 1/2. with different estimation methodologies. So Jim explained very, very well the difference between the old style estimation procedure and the new version of this, consistent estimation of this parameter. In my opinion, I'm still quite skeptical. I would like to enter into details, but not on this talk. This talk we just take as an input the general framework with a generic age. So in the Heston model here, this is the integral version. So instead of giving the differential evolution of the volatility, we just take the integral version of the volatility, or the infinitesimal, sorry, in the instantaneous variance process. And in the rough case, we just replace the integral version by introducing a kernel. So this particular power kernel gives the rough path in the case where alpha belongs between 0 and 1, or classical fractional Brownian motion, not with rough paths, from alpha, which between 1 and 2. So if you let alpha range between 0 and 2, you have all the possibilities, so old-fashioned and the new paradigm of rough volatility. So this is a new version of the Heston model, where apparently there is no fractional Brownian motion in the story, but a closer look reveals that you can always decompose with, for example, the Mandelbrot-Van Ness representation. You can represent the fractional Brownian motion in terms of this particular power kernel in stochastic integral. So the idea here is, okay, if you want to just look at what happens nowadays in finance, you should be interested in this alpha, so range in this interval, but nobody says that you can also provide some interesting numerical schemes for the old case. Okay. Well, now the idea is that, okay, for the classical Heston model, we have the characteristic function which can be found explicitly by solving a Riccati equation, so quadratic ordinary differential equation. And according to the terminology of Omar and Mathieu and Abi-Jaber co-authors, who investigated not only the problem of finding the characteristic function of the log price, but also a joint transform involving also the volatility, if you want. So it's quite more general problem associated to some Volterra processes. You can end up with exactly the same kind of Riccati equation, but instead of having an integer differential operator, you have a fractional differential operator now. And the idea is that originally Omar and Mathieu found this equation by taking the limit of some Oakes processes converging under suitable statistical assumptions on the fractional Brownian motion with h less than 1 alpha. My conjecture, my answer is that if I can change slightly these microstructure assumptions, also statistical assumptions on the data generative process, so the underlying process here, in order to get another convergence, but with a process with h greater than 1 alpha. It's an ansatz for the moment. So I would like to see more closer the story, but this is not the subject of this talk today. So now Abi-Jaber, Larsson, and Pulido found a very nice way to deduce the same Riccati equation using the same methodology, the same technology as the generalization of the Feynman-Catch formula, if you want, by involving a differential operator, which includes also memory in the story. So, of course, the framework is no more Markovian here, so you have to pay attention, to be careful how to take expected values and, in general, all the operators. But it is that you end up quite safely to a very similar equation here. We have also to pay attention to the boundary condition in particular, so I will spend some words on the integral operator here. So according to the usual case, which is useful in finance with the initial condition equal to 0, you can also generalize this thing according to the Volterra equations. And we are able to handle both of them. So in the paper we consider the first part, which is most most useful for financing the initial condition equal to 0. There is also a result which is much more involved and requires a lot of work in order to prove the convergence we will see, and the convergence domain for the corresponding discretization scheme, also for the case of Volterra processes, but it's up to my understanding. For the moment, there is not really financial application on that. It's just a numerical result. Okay, so here the fractional Riccati equations involve the model parameters as well as the, if you want, the Fourier frequency of the characteristic function. And here U1 is a complex number, and typically the real part, imaginary part, should satisfy some constraints in order to, well, to be well integrable, and typically the real part of this guy will be quite high. So in order to be integrated by Fourier transform over a numerical integral ranging from, something going till 200, 300. So, this number is not innocent. It plays a role in the numerical scheme. Well, what do we do in this paper? We just take as an input the fractional Riccati equation here, and we try to provide some efficient numerical scheme in order to get the solution. Because we will see the benchmark so far is given by something, the Adam methods, which is more or less a quite sophisticated numerical discretization scheme involving memory, which is very, very slow, and it's also not very precise, so mostly for short maturities. Here we would like to consider constant coefficients. There are journals devote their attention to the fractional Riccati equations, and when the coefficients are not constant, of course, problems become much, much more involved. Here, we just take the financial problem with constant coefficients, but potentially with different initial conditions here. So the boundaries can be different according to the particular problem we consider. So the solution can be written in terms of a power solution, not a classical power solution. Of course, it should be a fractional power solution. And we will find the convergence domain of this fractional power series solution. And beyond this, the convergence domain, we suggest an hybrid scheme. So, in some sense, a mixture of power series expansion and a discretization scheme. And we will exploit the advantage of having a closed form solution for the power series and the efficacy of the numerical scheme in terms of discretization. Well, for the moment, we focus on the so-called rough for the talk, but in the paper we will consider also the other case, which is in principle not so different. We have to pay attention because here there are some explosions which can appear in the rough case, which is no more the case in the classical framework where h is greater than 1/2, but the methodology more or less is the same. So we can really apply the same techniques also to the classical case, but we focus first on this fashion case of rough volatility. Just a couple of words in terms of the integral operator here, but also in the mini course given by Jim, it was very, very clear in the intuition. Here the integral operator as well as the derivative operator is a natural generalization to the real case where you differentiate or integrate according to a real and no more integer exponent. That's the idea. Once again, according to alpha, you have to pay attention because you have some singularities, so explosion, etc., etc. Okay, but it can be handled nowadays. Well, the nice properties of these operators is that if you apply the fractional derivative operator to a power function, you get exactly this expression still in terms of power function. So it is closed under this kind of operation. So fractional derivatives of powers are still power. And this gives the intuition that maybe the fractional power series may work. That's the idea. Of course, the derivative, the fractional derivative of a constant is no more a constant in this case because you have to take into account the memory. So there are some non-naive phenomena appearing here, but okay, it's well understood since a long time ago. So the idea is quite simple here. Since the family of powers are closed under this particular fractional operator, we can, for example, conceive this kind of development here instead of the classical one. And we will see that it works very well. And in the case of, the simple case of rough Heston model, it is enough. In the case of Volterra equation, it is not enough in the sense that we need something more. So we need a doubly indexed fractional power series expansion. And this also in the spirit of another related work of Antoine Janquier and co-authors, who also understood this story that a single indexed power, fractional power, is not enough in the case of Volterra equations. So we share the same framework here. Okay, so this is a very ugly slide, but the intuition is quite clear. Basically, we have a function satisfying a quadratic equation, but we have also a guess for the form of this equation. So we just apply the differential operator to the function psi. So we get a series of fractional series as function, and we use the Riccati equation satisfied by psi, and we identify term by term. So it's very simple. So we just identify term by term, and we arrive to a recursive system where we have to be very, very careful to the boundaries. But it is that you can identify the coefficients of the series just by comparing the functional form of the fractional power series. And the solution so far is exact if you go to the end, of course. Moreover, from classical analysis, it is well known that for this kind of power series, the convergence of the series is guaranteed, is granted until a certain maximal domain. Of course, we have to be careful because the domain of the existence of the solution may be larger than the one given by the series. And this is a typical effect of, for example, if you have an analytical function, think about, for example, logarithm of 1 plus x, you can really get something in terms of series beyond 1, but not before -1. So the idea is that you need something in terms of a constraint in terms of the absolute value of x, of z, of the argument, even if you can speak about the existence of the solution beyond 1. So this is a sufficient condition here. You can have a larger domain of existence, but we would like to work under the sufficient condition in order to grant the convergence of this series. And we spend a lot of time and energy in determining precisely the domain of convergence, because this is a crucial step for our hybrid method. If you are really able to be sharp in the convergence domain, so you can know exactly where you have to stop just a little before in order to avoid the phenomena like explosion, etc., etc. Well, here there are the analytical results for the upper bound and the lower bound for the expansion in series. So this is the lower bound, and this is the upper bound, involving model parameters, involving the parameter alpha, so implicitly the Arst exponent, etc., etc. This is, if you want, a closed form estimation for the lower bound, as well as for the upper bound. What we need here is, of course, the lower bound, which is in particular not real efficient because we can easily show that if in the case, for example, where there is no quadratic part, the Riccati is no more Riccati, becomes a linear equation for which the domain of convergence is plus infinity, but still in our approximation, in our estimation here, there is no way to go to infinity. So it's not efficient, but still sufficient for us. Well, what happens to the error of this series expansion? We can also manage the error in terms of something involving, once again, the Arst exponent. So also, the remainder of the series can be managed analytically, not just empirically. Okay, so in order to do pricing, what we need is to compute the characteristic function. The characteristic function involves the solution of the Riccati. We need also the integral. We need, a couple of integrals involving the solution of the Riccati. But as soon as you are able to solve the fractional Riccati, computing the other integrals is quite easygoing in the sense that you apply the integral operator and everything goes well in terms of fractional power series. So the triplet can be computed instantaneously as soon as you have the solution of the fractional Riccati equation. And if you have the capital psi, you're ready to do price in the sense that you have explicitly what you need in order to invert by Fourier transform. And you are ready to give a price. Well, now the idea is that unfortunately the power series doesn't converge always, of course. We defined an upper and lower bound, so the natural question is, okay, and if the maturity of your option is beyond the convergence domain, how can we do? Of course, this is when the hybrid scheme comes into the story here. So for the moment, we have to determine a trade-off of the number of terms in our series in order to get a reasonable result for so where to cut, basically, the series expansion. And we have to also to find a trade-off in terms of the threshold before the maximal domain of convergence. So this is the estimation for the convergence domain. We would like to stop a bit before. So we multiply by a parameter theta to be determined in order to be sure that the maturity of our option is less than this threshold. If it is the case, no worries, you can use the power series expansion, and the solution is exact. And then it's just a question to decide the number of terms in your expansion. If it is not the case, because your maturity is beyond the confidence level for explosion of this series expansion, in this case, you need an hybrid method. What would we do is basically a procedure called the Richardson-Romberg extrapolation method with some refinement. I don't want to bore you after the quick lunch with the details of the multi-step extrapolation of Richardson-Romberg, but basically it's a discretization method where we have to, here is just a comment about the choice of the number of terms in our series expansion, and we found that with 250 terms in the series, we basically reach the convergence. But what we
with reasonable parameters in this model.
Sorry?
With reasonable parameters, what size is T for which you can use the power series?
We will see later in a, we borrowed exactly the parameters of Mathieu and Omar. So we have the exact comparison. So for beyond the convergence domain, we can use basically a discretization method where we have to choose the discretization step, and we consider a k0 in such a way that tk0 is just before what we decided to have to define as a confidence level for the explosion time, and the subsequent one. No, so now we have the discretization scheme from the explosion or just before time till the next step in terms, once again, of a discretization of the integrals here. So the formula is huge, but okay, there is nothing really deep in the story. We can just discretize in the spirit of what Adams did in his algorithm, but with a different power series here, for example, due to the fact that we have fractional powers. Okay, so I skip the details. There is the possibility to improve the convergence of the scheme. So through the multi-level, in particular, the multi-level, how is it called? the Richardson-Roberg of order 2, we can reach a speed of convergence which is quite satisfactory, but we can still improve the methods by involving the level 3. So there is an algebraic simplification and a small miracle happening in this discretization procedure of the Richardson-Roberg method in order to get a convergence of speed n-2, which is very important in the sense that now also in the long term, when you discretize the series or the process, you reach the convergence much, much faster than the Adams method. So a priori, it has the potentiality to be more efficient than the Adams method. Of course, we have to speak about numerical results now. Okay, so the first test we do is just to borrow the parameters in Omer and Mathieu. So what they published recently in Mathematical Finance, that seems to be calibrated also on S&P. We just consider the mapping of our parameters with their parameters, and here we have to just choose the frequency parameter of our characteristic function, and here we just take 100, just one target value for U1. And we consider a set of maturities here, so ranging from 1 day till 1 month. Okay, what is very nice is that the computational times is very, very low, in the sense that, welcome aboard. So it takes something like 200 microseconds, so 10 minus 6. Okay. And this is the answer to Jim. The convergence radius is always beyond capital T. So it means that for these particular maturities, and look at, we are considering short-term options in this case, so till 1 month, there is no problem. So for the short-term smile, basically we can always use the power series expansion. That's the. Of course, this was an ad hoc example in order to be sure to be able to always employ the fractional power series expansion. But of course, we would like to understand which is the performance also beyond. So we would like to test also the hybrid method now. And the idea is that we consider a book of options with the same methodology. We borrow the same parameters as before. We set for Adam, we would like to compare with Adams' method. And we consider the discretization of Adams' method in order to get a distance with our prices in terms of implied volatility of 1%, which is a huge, a huge bias, but still we consider to be satisfied if the difference is below than 1% in terms of volatility. Well, what we find is the following still huge table, where the same of Mathieu, 0.16, something like that, 0.16. So we are in the rough contest here. So here we display the results. So from a book of options where H stands for the Adams method, H for the hybrid method, A for Adams. And we look immediately some stars here, and the star is due to the fact that for short maturities, sometimes the convergence of the Adams method is not satisfactory at all in the sense that it leads to arbitrage opportunity. So it seems that the price is even greater than the intrinsic value of the option. Okay, so Adams is not only slow, but is very, very biased. So at the beginning, it leads to some potentially arbitrage opportunity. Of course, this holds true only for very short maturities. Then this phenomenon disappears. This is for the double star. You see also the Adams method is very, very fast. So it's comparable with ours. Sometimes even faster, but I mean, it's useless to be faster if you are not precise in this case. And for 1 star, it means that we were not able to push the Adams methods to converge in order to get at most 1% of difference with the implied volatility. Even if you discretize a lot your process in the discretization procedure of the other methods, you made more and more dense the time grid, you don't converge to something which is similar to our price. And in the short term, I repeat, our solution is, we can say, exact. We choose just the truncation of the series till 250 terms, but we reach after 200 terms almost a flat value. And so the idea is that, basically the intuition is that the process has not enough time to adapt to move for the volatility. In some sense, even if you make more and more dense the discretization in the short term, nothing happens basically. On the contrary, in the long term, something happens, so you can improve the other methods by introducing additional steps in the discretization. But still you see the difference in the sense that in order to force to have a different implied volatility quite similar, we are still below the second. These are milliseconds, so 10 minus 3 seconds. And you see the numbers here about the other methods. I mean, it's unfeasible. It's far greater than 5, sometimes also 10 minutes for just one price. Okay, so just to repeat, in the short methods, in the short maturities, there are even some arbitrage opportunities for the Anders method, so which means that the method is not precise at all. In the long-term maturities, we have the problem that we have to choose the correct trade-off for the numbers of time discretization steps. And for example, 2 years, it requires more than 4 minutes, and we have, okay, standard laptop as you want, but in our method, is less than 1 second, so still feasible. So this is about the speedy. It would be interesting to compare with your method, Jim, because your method seems to be closed form. So it doesn't care about the horizon, but in this case, so the battle will be in terms of the precision of the method. So it would be interesting to compare of that. Okay, this is basically what I wanted to tell, but since Bruno is here now, just to remember a very short story about you and me. You, of course, you forgot this story, but in 2008, Marco Vellaneda invited me. At that time, I worked on visual processes, invited me to give a talk at Courant Institute. It was September 2008. And then Peter Carr knew about that. I was, okay, Martino, come also to Bloomberg to give a presentation of visual processes. And you were there in the floor. And I was very enthusiastic about visual processes, so I explained the table in Bloomberg, beautiful context in New York. But you didn't care me at all. You wanted, and it was the 16th September 2008, and you were on your laptop. I didn't understand because I had no Wi-Fi at that time, so I just came on Sunday for 14 September, so the Monday 15 September, and then 16 I gave the talk. And I didn't understand why you were not so, attentive to my talk. In the afternoon, I understood. Okay, so I would like to thank you for your attention, and of course, I wish many, many pleasant things to Bruno in the future.
Thanks, Martino.